Okay. Let's see what we do today. Okay. Last class, we started talking about probabilistic perception is a new way. Look at problem of perception and robotics. Because in reality, everything is probabilistic. We need to find a way to model this probability, distribution, random variables, and stuff. We started talking about actually some probabilistic rules. Like chain rule, for example, was a very important one. And also we talked about Bayesian rule or Bayes rule. And after that, we mentioned about Bayesian inference. We said if you are talking about probabilistic things, you need to kind of predict some variables that are not visible. We call them latent variables. We can use Bayesian inference to do that. In Bayesian inference, you are kind of computing posterior density, if you remember. We write them up to make it more solid. So posterior is the main point. Posterior means sometimes posterior density, we call it. Posterior is probability of unknown given something known, like measurements, for example. And X is something that we call it latent, because it's unknown, latent variable. Sometimes it's latent function if you do function approximation. Like for a neural network, we also have kind of things, but a neural network is all based off data-driven method. But in here, we are doing that probabilistically. Okay, so the main point of all of perception in robotics is this posterior density. This posterior density gives us everything because we just need to do some optimization to do inference. Inference means getting data out of this probability and actually predict these latent variables based on probabilities. So what we're gonna talk today, we're gonna see, because this probabilistic formula sometimes is so complex and complicated because of relationship between these random variables. I told you many times that relationship is the hardest things to model in reality, in everywhere in the world. To make these relationships at least understandable, we want to find some graphical model to present them. When we graphically present them, we can understand them better, and we can work on that and do some algorithm to optimize it, to make it nicer and better and understandable. We're going to talk today about one graphical model called BayesNet. BayesNet or Bayesian network. And later on, next class, we're going to go for more advanced of Bayesnet. BayesNet is just the start. It's not really actually good enough for our work. We're going to go for something better than that called factor graph. They are all graphical way. Graphical way to do what? To do to model this posterior density, to model these probabilistic formulas. So that's the main point. If we can show them graphically, we can understand them better. Let's do example here to just set the stage for the class. Imagine you have a robot that is actually moving from one position x1, for example, going to x2, and then going to x3. And there is some, we call them lens marking, like vol, for example, here. We have one lens marking here, L1, another one, L2, another lens marking that's showing. Lens marking are also unknown. We don't know them, but we can actually measure a distance from them to localize ourselves. At the same time, we are localizing them as well. So the measurements is something here. We call measurements, we always use Z for that. For example, we have one measurement here, and we read these measurements based off that landmarking, like a wall, and move forward. And in this state 2, for example, we read from another wall, maybe the same wall, another measurement, we call that Z2, for example. And in X1, also we have some other sensors inside, like some odometry or IMU that we read measurements from that too. This is another Z3. So this picture, we are thinking that's showing more and nicer information than write something like that. Like mathematically, if you want to write this, you need to write probability of x1, x2, x3, L1, L2, Z1, because they are all random variables. Z2, Z3 is equal to, you need to say this is equal to probability of Z1. I'm just going to write a little because it's a long list. I want to just show how this graphical representation showing all of this relationship with just a picture. Probability of x1, probability of x2, this direction is important. x2 given x1, probability of x3 given x2. I don't write them randomly, I'm just writing them based off the relationship. Right now, these three positions, they are following a Markov model. Markov model means that the position x2 is just dependent on x1, not x0, for example. And x3 is just related to x2. This kind of relationship called Markov chain that I'm going to talk about later on. However, probably you know that. And then let's go for other, like probability of, multiply, like lens marking. L1, probability of Z1 given L1, X1, and so forth. And I need to write another line to finish it. So all of these relationships and conditional probabilities just can summarize in a picture. And the main point is that in this picture is this is a direct graph. Something I forgot to put direction. This is a direct graph, and there is no loop in this graph. This graph called actually BayesNet or Bayesian Network. Today we're going to talk about that. Whatever I'm going to talk about, this network. How you can write from your model, how you can model your perception using a graphical way. However, this model is not perfect, so we have better method, that is factor graph, that we're going to talk next class. But because this is the base, you need to know how this relationship works. to go for other methods. Okay. Okay, let's get started. This was just, I wanted to tell you what I'm going to talk about today. And that's a Bayesian network, because it's a network based off this conditional probability. Before going more, I need to clear what is landmarks. Landmarks is important because most of the time you don't use the name of that, but normally you are using that, but you didn't call it landmark. Like, for example, when you want to localize yourself, robot wants to localize itself, it's using walls around it, using some objects around it, some specific things around that they have some specific shapes or features that you know those things. So that's why landmarks is kind of prior. You know, you have some information about it. Anyway, landmarks are things that exist independently of the robot. They are not dependent on robot. Measurements is dependent on the robot because the position of the robot changed the measurements, of course. We have so many things. So measurements is depend on the robot position, and even depends on setting of the sensors. Like, for example, you have 4 sensors around the robot. If you have 4 sensors, they have different measurements. They make you different measurements. So the setting, the topology of the setting of the sensor is important for sensor. But position of the landmark, for example, landmarking is just sign. Yes. Like a stop sign. This is considered landmark. Or in a building, for example, a wall, for example. I wrote here, right? A traffic sign. A building corner can be just a landmarks, or any other features that is in the environment and is important for us, and is unique, kind of unique. And what we're gonna do with that, we're gonna use them as a reference point. We use landmarks as a reference point, and find our position based off them. At the same time, we are predicting them as well. They are also random variables. So landmarks are also random variables. Z measurements also random variables, and X is our states. They are all these two consider kind of states as well, but Z is considered measurements. And Z is related to X and L. If you want to show graphically, we always say Z and X coming to Z. L, and so it means Z is kind of distribution of Z is a probability of Z given X and L. This is called a likelihood. Anytime you are talking about probability of measurements, you're talking about likelihood. That's called likelihood. Anything related to probability of measurements is called likelihood. Likelihood of that measurements. We want to tell how likely is this measurements. Like, for example, you have a landmarking of this wall and a robot is here and finding the distance and get some measurements using one of those sensors, and we want to see how likely is the position of that landmarking. How likely is that? If I computed 2 meters, is it 2 meters exactly or 2 meters and 5 centimeters? How likely is that? How much it has noise? How much it has variation? How precise is that? So that's called likelihood. Anytime we are talking about Z, we are talking about measurements, we are talking about likelihood. Likelihood is that. Okay, so this is just notations that we need to know. So the landmarks are those things. They are not dependent on the robot measurements. And they are like independent, but they are part of or random variables. They are part of unknown random variables that we need to use them. Okay. But measurements are different. Measurements are observations. Measurements are actually coming from sensors, coming from position of the robot, coming from landmarking position, and also they are depend on geometry of sensors, and also depend on the noise that they have. So the measurements depend on these things. Depend on 4 things. The measurements that you are, for example, measuring the distance to the wall, that is a landmark. It depends on the landmark, depend on the position of the robot, depend on the setting of geometry of the sensor, and depend on the sensor noise, how this sensor is precise. Depend on these cases. So the measurements and landmarks are clear right now. About measurements, we're going to talk about that. Measurements are very important in perception. We're going to talk about the model, actually, measurements model. We have measurements model. Like how we have a state model, we also have measurements model. A generic method for measurements model. We're going to talk about that. So anyway, measurements are not part of the vault. It's actually something that we receive from sensor. And most of the time, measurements is a nonlinear function. Like, for example, nonlinear function of x and L plus some noise. That is, noise can be anything. We mostly consider that Gaussian. When we are talking, sometimes when we don't know the distribution of something, we just consider it Gaussian too, you know. Or it's too complicated. To just make it simple, we just consider it Gaussian. So that's the measurement model. This formula is made, and that H, sometimes if it's linear, is a matrix. Like, for example, in Kalman filter, we consider H as just a matrix. And sometimes it's not linear. It's not linear. Okay, so that's important. So that's the difference between landmarking and measurements. But what is generative sensor model? This generative sensor model is actually the reason of using graphical model. Because in the method, the model that sensors working is based off that, based off some position of the robot, based off landmarking, based off the environment, setting of the environment. We are generating those measurements. So normally measurements coming from them, from L, coming from environment, coming from position of robots. So in this relationship, that's why they call it generative model, but normally we call it measurements model. And as I explained, it's just coming from this formula. H of x L plus some noise creates measurements. Sometimes we call it Y as a measurement, sometimes Z, but mostly Z. Z is showing measurements. So in this model, X is the position of the robot, L is the position of the landmark, and H is measurement prediction function. Is a prediction function or measurements. There's another name for that if I remember. Yeah. So yeah, I don't remember that. But measurements function or measurements transition. Sometimes if it's matrix is it just transition between state and measurements. And we need that a lot. We need that a lot. This is kind of bringing states with measurements in the same space. H makes these two x's and measurements in the same space. Like for example, imagine x is in Cartesian space and z is in polar space. If you are using LIDAR, if you are using radar, the data that give you is angle and range is polar space, another space. You need to bring it back to the space that x and L are there. They are in Cartesian space in x and y. So change that. H actually changing this transition as well. Okay, so the H acts as a transition function. So measurements prediction or transition is kind of transfer from some space to another space, from a space of measurements to a space of states. Not always states and measurements are in the same space. That's an important point. And we also have uncertainty, this noise coming from that. Okay, anyway, but this is the generative sensor model or a measurements model. When I'm talking about sensor, the better name for that is a measurements model. Measurements model. Model of measurements. So this is the model of measurements. And but what is this represent? This is representing this generative sensor model representing relationship between Z and X and L. So it means probability of Z, it depends on X and L. If X and L given, then Z can, probability of Z can get computed, you know. So the Z is kind of depend on this distribution of, and that distribution called what? What that's called? Posterior or likelihood? Likelihood. This is likelihood. What is posterior means?
After.
What is the posterior?
X given.
X given. Good. If X is there, it's posterior. Yes. If X is there, it's posterior. If it's Z is there, is likelihood. And here is when the Bayes formula comes. And we are talking about Bayes-net, but there is no Bayes. Bayes coming here. Bayes coming in this step. Bayes saying probability of like posterior density X given Z. When I'm talking about Z, this Z can be a lots of other things. Z1, Z2, Z3, weights of the sensors and the environment can be a lot. Is equal to proportion. When I say proportion means we're going to remove the other things that are not related to X. It's P of z given x, that is likelihood, and p of x. What is p of x means? Remember last class? Prior. And prior coming from dynamic of the robot. Why, I will tell you. And this is likelihood. So the posterior is hard to compute because it's something unknown, but we know likelihood of measurements because we have sensors. That's given. Well, this likelihood is given. And this is given too, kind of, because it's prior information that based off your belief, you believe that robot was here and supposed to be there because it was moving with this speed based off the dynamic. So you can have that too. So the prior information is kind of a prediction that robot is supposed to be there. So with these two information, you can compute something unknown. That unknown is posterior density. And that's all coming from Bayes' rule. That's why all of this story called Bayes. And Bayesian modeling and Bayesian networks and factor graph, and they just make another area of studying in robotics and engineering and computer and stochastic and probability called Bayesian method. Bayesian method is just a method of look at the problem in this method, Bayesian way. Even method of thinking in a Bayesian way. Anyway, somebody talk about, okay, to think about this as a Bayesian way. It means you always consider some predicting and some likelihood and some prior, and get your prediction based off these two. Based off these two, make your prediction based off these two. Kind of you are updating your belief. You believe something, but you don't know 100%. You can update it. How? With measurements. With new information, you can update it. Okay, so that's a very nice way to look at the complex problems. Good. So that in a better way. Oh, no time. Okay, let's go. Bayesian network. So the Bayesian network normally is a graph. But this graph is a cyclic graph, so it doesn't have a cycle, and directed. And nodes are random variables, and edges are actually probabilistic dependencies. Like when we say, okay, x is z depends on x, means the direction is to the x, or the relationship between landmarks and z, for example, is this way. So it means z, to find z, we need L and x. So this relationship showing in a Bayesian network. This is Bayesian network. And each node has a conditional probability, as I mentioned. Okay, so most of this stuff I already mentioned. But the point in this graph is probability of each random variable is given based on all the parents, and because it's direct graph. If there is direct graph, so you have lots of parents, so probability of xi is given all of those parents. Okay, so we can extend it for so many things. So I just talk about all of these things. I'm just gonna pass them and just do one example because I already talked about all of this. Yeah, I already talked about them. In this example, I don't know why I put lots of slides, but I already talked. In this example, you can see those relationships. It's the same example, not same, but almost similar example that I started at the beginning. As you can see, probability of X and Z, when I'm talking X, means all of X, not just this X, means X1, X2, and Z, Z1, Z2, and this can be break down to that. Okay, I think you are, you want to go to the other classes, you have multiple classes. I have two. So that's fine. I can talk about this next class at the same time to the factor graph.